All right, so picking up where we left off, we have the Big Bang making hydrogen in the form of protons, and then those fuse to form helium. So there's a particular ratio of hydrogen to helium that the Big Bang forecasts, the Big Bang models forecast, which is what we see. And then you'd wait a long time, 400 million years before you get to, well, 380,000 years, then you get electrons combining with the protons to form atoms, the first hydrogen atoms, and the universe becomes transparent. And then that's the radiation that we see. That's the microwave background. Then you have to wait 400 million years for stars to form. And then stars are the factories that turn this hydrogen and helium into more complex elements, right? So the idea is, as the universe ages, the principle of chemical evolution is that the amount of hydrogen in the universe always goes down. Why? Because there's no source of hydrogen anymore. The only source of these protons was the Big Bang, right? The beginning of the universe. We never said when stars are going through their lives, they're not making hydrogen. They're composed of hydrogen, and they're using that hydrogen to build new things. But the amount of hydrogen in the universe is going down. The amount of helium in the universe is I'm going to be non-committal. You can convince yourself it's more complicated. You might think the amount of helium goes up because hydrogen makes helium, fuses together to form helium. But then we have to be careful because helium is also used and destroyed in order to build elements further up the chain. So immediately it's maybe not clear what happens to the total amount of helium. And it's not terribly important for us anyway. The other elements, over time, the percentage of all the other elements goes up because they are generated in the stars, right? Stars are constantly using hydrogen and helium to make all the other elements. So as the universe ages, the amount of hydrogen goes down and the amount of all other elements goes up. And then when stars evolve and blow up, right, they return all that stuff back into the interstellar medium and form new stars. So the sort of the soup of the universe is being enriched by these stars. They're the factories that generate all the things on the periodic table besides the hydrogen. Okay, so then you get to the present day. And is there anything about the expansion that tells us what the future holds? And here's what I mean. It didn't take long after we discovered the expansion and the Big Bang that people wondered, well, what's going to happen, right? Does the universe just expand forever, or what's going to happen in the future? So the idea is there's a couple of possibilities. Imagine just taking a ball and throwing it up in the air. The reason that the ball comes back down again is because there's enough mass. The Earth has enough mass and enough gravity to stop its motion up and bring it back down. You could imagine throwing a ball, or maybe you're on a small asteroid and it doesn't have enough mass. So if you throw the ball, it could never come back down, right? It could escape. That's that idea of escape velocity that we talked about before. So you could imagine that the universe, maybe there's a couple of different ways this could go. Maybe the universe will expand forever because the universe is not massive enough to stop the expansion. Maybe the expansion is fast enough to overcome all the internal gravity of the universe pulling back the other direction. Maybe. That's a possibility. The other possibility is that the universe is massive enough, and so just like a ball you would throw up in the air, the universe gets out to some critical size, and then all the gravity makes the motion stop, and then it comes back down again. And so the universe might come back in what used to be called a big crunch. And maybe that fuels another expansion, right? So maybe there's this oscillating forever, oscillating and collapsing universes. Now, the universe that keeps on expanding forever, but still slowing down because gravity is still slowing it down, but it escapes in some sense. So it keeps on expanding forever. That's called an open universe because there's no limit to the size of it. It just keeps expanding forever. And a closed universe is one that goes out to a certain size and then recollapses because there's enough mass, there's enough gravity. So no one knew, you don't know off the top of your head which one it is. Is it open or closed? Is it going to come back together in a big crunch, or is it going to expand forever? So what happened was, in the 1980s, this started to happen. We started taking big surveys to see how much mass is there in the universe. Is there enough mass to cause everything to collapse back again? And we found some interesting things. One of them was called dark matter, and we didn't talk about dark matter. Basically, it's stuff that's not atoms. We actually have no idea what it is. It's still a big mystery. Nobel Prize is out there waiting for someone. All we know is that it's strange stuff that obeys the laws of gravity and pulls on other things. And they hold the galaxies together. Dark matter holds the clusters together. And the problem is, though, that by adding together all the mass that we see in stars and galaxies, plus all the dark matter that we can find, you still only get about a third of what's necessary to make the expansion stop. So as of the mid-1990s, the idea was that the universe will just expand forever, always slowing down but never stopping, because there's not enough mass to sort of close the universe in some sense. Okay. Then in the late 90s, there were observations of supernova 1s, supernova type 1s. Remember what those were? Those were white dwarfs, 1.4 solar masses that collapsed and exploded. And they're very, very bright, right? They're one of the most, one of the brightest events that happened in the universe. The cool thing about those is that for our purposes, it's always the same object that explodes. Type 2 supernova are, they're a little different than this because those are massive stars that explode. And massive stars can be anywhere that explode in supernova could be 10 solar masses, could be 100 solar masses, right? So they could range in brightness. The cool thing about type 1 supernova is that it's the same object. It's the same stick of dynamite that's exploding all the time. It's a 1.4 solar mass white dwarf that collapses and explodes. It's the same object every time. The value of that is that it explodes with a known luminosity. So it's what we call a standard candle. It's of known brightness. So when you look out in the universe and you see one of these, all you have to do is just look at how bright it appears. Remember that relationship between how bright something is and how bright something appears, and that tells you the distance. So we look at these supernova 1s, and by looking at how bright they look, then we can instantly calculate how far away that happened. So we use these as sort of distant signposts in the universe. And because they're so violent, we can see them at a great distance. So people started to use supernova type 1s to measure how far away these galaxies were, and to measure the Hubble constant, to measure how fast the universe is expanding. And starting in about 1998 or 1996, and it took a couple of years for this to be really convincing, what we found was something really interesting. Here's what we wanted to do. We wanted to settle the debate, right? Is the universe going to for sure just expand forever, or is there enough mass to get it to? And even if it expanded forever, the idea was it was going to slow down. And in fact, I went to one of these conferences, and what they were trying to figure out was what they called the deceleration parameter, right? The rate at which the universe was slowing down. And they expected it to be slowing down, and they called it the deceleration parameter. And then what happened was, when we actually took a look, it turned out that the universe was not slowing down. The deceleration parameter was negative, which surprised everyone. And what that means is the expansion of the universe is getting faster. I'm going to write that down. The expansion is accelerating. We couldn't have been any more surprised than if you just toss a ball up in the air and the ball doesn't come down, the ball just keeps on going faster and faster away from the Earth. No one expected this. This was very strange. It doesn't stop us from giving it a name. What is that force, that sort of anti-gravity force that's pushing the universe apart faster and faster? We call it dark energy. This is not the same thing as dark matter. They're two totally different things. It's unfortunate that they sound alike. But this thing we call dark energy. It's the force that pushes the universe apart. The bigger the universe gets, the faster it expands. What is causing it? What is dark energy? Nobody knows. It, like dark matter, is a complete mystery. Big Nobels are out there for people who figure this out. We have no idea. All we know is that the universe, the expansion of the universe is accelerating. We have no idea why that's happening. So it's an exciting time to be involved in this branch of science called cosmology, the study of the universe as a whole, because no one knows why this is happening. So I will leave you with that mystery.